Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing our study of Chapter 7 on equations of state, and in this little lesson, we're going to be looking at group contribution techniques. Group additivity methods or group contribution methods basically are based on some recognition of some general patterns. So here in this table from our textbook, it's a comparison of normal boiling points for saturated hydrocarbon isomers. So they've looked at normal butane, normal pentane, normal hexane, heptane. So the increasing values of carbon in our basic alkanes and in branched versions of those, isomers of those. What you notice is that as the number of carbons increases, the normal boiling point increases, both for the linear compounds, butane, pentane, hexane, etc., and for the branched version. However, in each case, the branched compound has a slightly lower value of the normal boiling point. This is sort of the motivation behind group additivity methods. What they look at is the size of the molecule and how they are attached to, each atom is attached to the next. There are formulas that are used for the Joback method, which is the group contribution approach that is in our textbook. And so for each of the various functional groups, so if you were looking at, say, propane, it's got two CH3s, and each of those CH3s are attached to each other, and those are functional groups. That wasn't propane, excuse me, that was ethane. If you go up to propane, you have the two CH3s on each end, and in between you have a C with two H's that's attached to those. So you'd have two of the CH3 end pieces, and then you'd have the C with two H's in the middle. And so those are your functional groups. You look up heat of formation, you look at boiling point contributions, critical point contributions, etc. And those then get combined using these formulas. Now, these are specifically for the Joback method. There are many others. UNIFAC and UNIQUAC are going to be some that you'll look at in Thermo 2, most likely. So these formulas here, critical temperature, I'm going to take the sum of all the boiling temperatures for my components, okay, each of those little functional groups. I'll add those together, I'll square them, I'll add them together and multiply by 0.965, and I'll take the difference between those two answers and then add 0.584. The reciprocal of that answer multiplied by the boiling point will give me an estimate of the critical temperature. Similarly, the estimate of PC for each functional group, added those together, that is going to be subtracted from 0.113 plus 0.0032 times NA, which is the number of these pieces. That expression added together to the -2 power, etc. If you look at this they did the compound CH3, CHCl, CH2, CHCl, CH2, CH, double bonded to CH2, then the functional groups are highlighted here. Some of them there's only one of, for instance, the CH3 on the left end, and some there are two of. CH2 shows up twice, and so forth. They've found the data. These are in the Appendix G of our textbook for each one of these and added those up. We could then apply these to the various formulas we had and estimate the critical point, the boiling point, etc. of these materials. So that's all we're going to do with this one. In our next video lesson, we're going to be looking at yet another equation of state, which is the virial equation of state. That's going to be our most theoretically justified equations. Thank you very much for your time.